Well, greetings, everybody. Here's a question that was sent to me by way of Ask My Instructor, and at least at the time I'm making this video this semester, it's from assignment 3.1. And we're given a function or a curve, whatever you want to call it, and the objective is to find out where the curve is concave up or concave down, okay? And find the points of inflection. So let me summarize a little bit about what we have and what we're going for. So here's my whiteboard, and I'd say, okay, well, here's the function or curve that was given. And though, as far as the math goes, the way that it works is the curve will be concave up if the second derivative is positive. So right there I wrote f double prime greater than 0. That means positive. It will be concave down if the second derivative is negative, and there will be an inflection point if the second derivative is 0. You can think of the inflection point as the transition between being concave up and concave down. So, to make a quick sketch, I'm not saying that this is what this function looks like. I'm just giving this as an example. There's a curve, and like in here, it's concave down. Okay, so I'm going to say like concave down, roughly like right in here. And here it's concave up, okay? So I write CU for concave up. But you got to think, like, at what point does it cease being concave down and start being concave up? Like, where's the point that's transitioned between the two of them? That's what the point of inflection is, okay? So I'm going to write POI, point of inflection. So when I go back to this question and it says, where's the function concave up and where's it concave down, and what are the point or points of inflection, that's what it's asking for, okay? If our curve were to appear like that at any region on it, that would be the part where it's concave down. If the curve were to appear like this on any region, that would be where it's concave up. But it switches, it transitions between being concave down and concave up at the point of inflection, POI. Okay, so that's the the short story behind it. Okay, well, let's go ahead and figure this out. It all comes down to the second derivative. So what I did is I found the first derivative using the rules that we've learned before in other lessons, and then from the first derivative I found the second derivative. Okay, that's what we need to analyze, because where the curve is concave up or down and where the inflection point is all depends on the second derivative. All right, so that's what we need to analyze. So look, how would you sort out then, where is the second derivative positive? Where is it negative? Where is it 0? What's the best way to sort that out? I'll say start with figuring out where the second derivative is 0. Because if you know where it's 0, you can test outside of that to figure out where it's positive and negative. Okay? So, okay, I'm going to have the second derivative. I'm going to set it equal to 0. I'm going to solve that somehow. So here's the second derivative that I just found. The way that I'll solve this for the video is I'll factor out a 12, and then I get 12 times x squared plus x minus 20, and then I can factor that as x plus 5 and x minus 4, and then that factorization gives me my solutions, negative 5 and 4. Okay, that's just one way that you could solve it. You could also use the quadratic formula. There's lots of ways, and I guess like right now I'm not insisting you do it any one way, but I want us to agree negative 5 and 4 are the places where the second derivative is 0. Now I want to summarize what we know then. So imagine the x-axis. Imagine you're scanning the x-axis. You're looking at this graph. Here's what you'd see. At the spot where x is negative 5, the second derivative, okay, so that's what's up here, would be 0. And at the spot where x is 4, the second derivative would also be 0. Now, outside of those numbers or in between those numbers, I don't know yet, okay? It's pretty easy to figure out the rest of this picture. Because think about it, remember the second derivative, it's a number at the end of the day, and it can be positive or negative or 0. I know where it's 0. So I'll just pick test points outside of 4 and -5, or in between 4 and -5, and I'll figure out what each of these question marks is as far as the second derivative being positive or negative. Okay? All right, so to fill this picture in, we do some test points, okay? So here's what I would do. I need to test in this region left of -5 to see what the second derivative is like. So I chose -6. I could choose any number left of -5. I could choose -6, -6.8, -11.43. It doesn't matter. And then I chose a number between -5 and 4, 0. Nice, easy choice. And then I chose something right of 4, 5. It's a nice, easy choice. But again, I could choose 6 or 7 or 23.4 or whatever. Okay. I take these test points, I plug them into the second derivative, and I get these numbers. Now, what these numbers are really doesn't matter. What I'm trying to figure out is the second derivative positive or negative. So I get 120, that's positive. I plug in 0 to this function, the second derivative, I get a negative number. Plug in 5 in, I get 120, a positive number. So that allows me to fill in the rest of the picture. Okay? All right, I know now at this point that the second derivative is positive left of -5, negative between -5 and 4, and positive right of 4. So okay, that's what the curve will look like. In very generic terms, it would look something like this, okay? Concave up and concave down. All right. Oh, sorry. That's incomplete. Concave up, concave down, concave up again, like something like that. All right. I can't claim it to be this exact shape, but it's got to like have these features as of concave up, concave down, concave up. And these points where it transitions, the point of inflection, that first one's at -5. And then the second one is at 4. Okay? So it's like concave up, but then right there is where it transitions to being concave down. And then right here it transitions to being concave up again. That's what this tells me. Because remember, if the second derivative is positive, it's concave up. If it's negative, it's concave down. If it's 0, we have a point of inflection where it's transitioning between being concave up and down. Now, at this point, I think we have what we need to answer the question. So let's look back at this question. Okay. Where it says, select the choice below and fill in the answer boxes to complete your choice. Okay. Now, I see it as my function, my curve, is concave up until you get to -5. How do we express that? Here, we're going to use interval notation. Okay. So it's like this curve spans forever left and right. There's no beginning and no end. So as we were to look at it, if we were to scan the x-axis, we would see that it's concave up from, well, I mean, what do you get if you go all the way to the left of the x-axis? We'll just say you get negative infinity, like that. There's no end to it. So we just say negative infinity to say that it goes forever. And then in the other direction, it's infinity. So that's why you see this answer being that, okay, it's concave up on negative infinity to -5 and also on 4 to infinity. Okay, that's what these intervals mean. They're just the parts of my little chart here where the second derivative is positive. That's all they are if you want to think of it that way. It's concave down in the middle from -5 to 4. All right, So when I put -5 to 4, that means from -5 over to 4, just like this means from -infinity over to -5, so on. So that's why the answer choice is A right there. Okay. All right. Now let's look at the second part. Select the correct choice below, so on. Where are the points of inflection? Okay, well, I figured that out already. Those are the places where the second derivative is 0. And they're at -5 and 4. Okay. All right. So it's like I have my answers. I know where they are, but it does say type an ordered pair. Use a comma to separate answers. So what I know is this. All right, that one of the points of inflection is at -5. That's the x coordinate, and I don't know the y coordinate. Okay, and then I put a comma. The other one is at 4 for x, and I don't know the y coordinate. It wants me to give points, so what it wants is the x and y coordinate. So how are we going to figure that out? When I say here that it wants an ordered pair or a point, what it's asking for is a point on the curve. Okay, so here's the curve. It's got points on it. I mean, I know that we're plugging numbers in everywhere over here, but the second derivative, when I plug numbers into that and complete this chart, it tells me where the curve is concave up and down. It kind of tells me the shape that way. All right, but the function itself is what makes the curve and gives you all the individual points that create the curve when you connect them all together. Okay, so what I have to do here is to find the points of inflection. I need to put in -5 into this function right here, and I need to put in 4 and see what I get the y coordinate to be. That would be the point, and that's what they're looking for. Okay, all right, so I'm going to do that with my handheld calculator real quick, and I'll write down what I get. Okay, so I use my handheld calculator and put in -5 into this function of 4, and I got those numbers. Those are my x and y coordinates for the points of inflection. Okay, there's 2 points of inflection. 2 points of inflection because the curve has this shape, and there's 2 points where it transitions between being concave up to concave down, or vice versa. Okay, so that's what we're looking for here, the points of inflection. Now I've got the points there. I put the question marks to be dramatic about what the y coordinate is. But now I know. Okay, so that first point, -5 for x, -2751 for y, and the second point, 4 for x, and -1446 for y. Okay, so those are my 2 points of inflection. All right, so we'll check it, and it's correct. Now, okay, so that's the whole procedure for doing this. Find the second derivative, figure out where it's 0, find some test points in between or outside of your 0 points. Okay, just plug some numbers in, see what you get, positives and negatives, and then you've got this chart that roughly describes the shape of the graph: concave up, concave down, concave up. Now you might wonder, if all this math just describes the graph, why don't we just look at the graph? And I'm open to that. Let's try it. So I went to a graphing calculator and I put in this function, and the points on it and the steepness of it is so extreme, it's hard to tell that it actually looks like this. Okay, I mean, imagine this but compressed together, so extreme that the climbing of it is steep, and basically you're looking at this. If you zoom out, if you zoom in, then you lose too much detail, and so it's just hard to tell looking at it what the shape is, where it's concave up, down. All I see is lines right here, and if I zoom out, it looks even worse. Okay, so it's hard to just look at it. It has a very extreme shape. That's why we analyze graphs and curves and their features just mathematically without looking at the picture. Sometimes the picture is too extreme to determine anything. Okay. All right, but yeah, it's looks like this just in a very extreme fashion. Okay. In any case, that's how we handle second derivatives in concavity. I did assume some things in the video, such as you know the rules for derivative and that you can solve this kind of equation. But like with any video, if there's something in it that I think is kind of a review topic that I pass over, then you can mention it and we can talk about it.